Okay, so what I'll do today is I will finish up the program that I started on Tuesday. Remember on Tuesday I was starting on a program to read decimal number so I can represent those numbers internally using base 2. So we'll finish that program first, and then we'll talk about maybe possibly a new homework assignment. But I definitely need to move forward to talk about the stack, subroutines, and also parameters as well as local variables when we get to the stack and subroutines. So that's going to be a big topic that we have to go through in the near future. So let me go ahead and go back to the program that we were writing the other day, which is still here, and it's called read decimal lowercase s. And this is what we have right now. Okay, it's not quite done, but the control structure itself is already done. I personally like to use this approach to interleave the code to be translated along with with the code that is in assembly. So this way, it's easy for me to associate and say, oh, this line is translated into these instructions, this line is translated into these instructions, and so on. I think last time I also talked about how to use git to do basically revision control. With a longer project, it's definitely worthwhile. With a small, short project, it's kind of. If you know how to do it already, it's not a big deal. If you don't know how to do it, the overhead of learning how to do it may kind of outweigh the benefits for in the short term. Okay, so let's go ahead and get started with this one. The control structure is done, which means the loop begin and the loop end and the condition to go back to the beginning of the loop. That part is done already. And I think the last topic that we talked about was this little b here, compare byte instead of compare long. And I talked about how something like this, you can have a program using the wrong width for comparison, and for the longest time it doesn't show any symptom. And then suddenly it just, it stops working. Because it all depends on what is next to it. If whatever is next to it is a 0, then it's going to work just fine. Because all the more significant bytes, they're all going to be zeros so it doesn't change the value of that one single byte. But on the other hand, if the variable next to it is a non-zero, then suddenly you cannot compare to 10 anymore, because the number represented by the 32-bit number is going to be a lot more than, in this case, 10. So you have to watch out for problems like that in assembly language programming, where you can, in C and C++ programming, for the most part, you can take that for granted. The compiler is going to do the right thing to make sure that the width of comparison and stuff like that will be all correct. Okay. So what we need to do now is to implement this particular line, which starts with a subroutine call to read. But since we are directly accessing the system, the operating system, we're not going to call read. Instead, what we'll do is we'll specify this is a read operation, which means we put a 3 into EAX. This is all coming from the big table that we talked about a little bit earlier, like this OS surfaces, and it's also discussed in the OS call in assembly language. So these particular notes will give you that information. The first parameter, which is 0, specifies standard in this case. We have to put it into EBX. The next one, which is the address of where I am. Okay, so in this case, the next parameter is going to be stored in ECX, and that is the address of where we will store that 1 byte that we are reading in from standard in. So in this case, we have to specify $ch because ch is a statically allocated byte. So this will represent this address. So we put that into ECX. The last one, which is the last one in the read call, that controls how many bytes we are trying to read from the standard in file, and that is stored in EDX. Now that we have set up all the registers, what is left to do is to invoke the software interrupt, because the software interrupt will go through the entire motion of kind of like a hardware interrupt, elevate the privilege level, go to a particular location in memory, so the operating system can say, okay, so what do you want? Okay, and the first thing the operating system is going to do is to look at EAX, because EAX is a number that indicates what kind of surface do you want. And once it identifies this is system surface number 3, which is reading from a file handle, then the OS will look at EBX, ECX, and EDX to determine what else is needed in order to complete the operation. Okay. When we come back from the system, when we come back from the software interrupt, EAX is going to be the return value. In other words, if I want to do exactly the same thing as the C code, I will have to move EAX into result, because that's what the C code is specifying, is the return value of read will be stored in a variable called result, because we have to refer to result at 2 different places. Are we doing okay so far with this code? The translation of this particular statement in C into these instructions in assembly. Actually, that's one more. So include the next one too. Is that okay? All right. So what is left to do is the conditional statement and also the calculation in the inside. The conditional statement, we first have to convert it into a different form to basically say, when do we skip over this code? Because that's basically what we want to do, is to determine how do we get around this code. We need result to be non-zero and the character CH to be not 10 in order to perform the then branch, which basically means if result is 0, okay, let me just write it exactly the way I said it. If result is 0, we can go to a particular label and we just call that and if in this case, because we only have one if statement. Okay, so we'll just directly write down the label, which is end if, over here. End if as a label is defined to be right after the conditional statement. There's one more reason for me to get out of the conditional statement, because if CH does equal to 10, which is the line feed character, I also want to skip around the whole thing and not to perform the calculation. So that's another reason to go to end if. So are we still doing okay here? I'm translating one single line in structured C code into 2 different lines in unstructured C code. This is the structured version, and this is the unstructured version along with the definition of end if itself. Are we doing okay so far? Okay. So I'm trying to do it step by step, but I'm not saving it.
I actually have a question about the $CH. Isn't CH a byte?
CH is a label, and the label is defined to be the address of that dot byte that we allocated in the dot data section. So that's why we have to refer to the immediate operand, because if you refer to it using without the $, then you're accessing the content at that location instead of the location itself. Yep.
So if the line that reads result equals read, if CH didn't have the ampersand in front of it, how would that change?
If CH does not have the ampersand, if CH does not have the ampersand and the code is still correct, that means CH is a pointer itself. So in that case, you will have to move LCH without the $ into ECX. Okay, good question. Okay, so now that we have the unstructured version of the C code, we can now go ahead and try to translate that into actual assembly code, and we are pretty much ready to do that because this is a comparison followed by a particular branch, and we can do that with a compare instruction followed by a conditional branch instruction. So once again, what I will do is I will do the comparison, CMP, in this case L, because result is a 32-bit thing. So compare long, question mark, and then we perform a conditional branch of some kind to end if, okay? So now we just have to figure out which question mark is which part of the original C code. In other words, what are we comparing here, and when do we branch to end if, okay, from the comparison. This part here is pretty easy. Oops, wrong place. This one is just Z because we are looking for equality. And if you want one value to be the same as the other one after comparison, you look at the Z flag, because when you subtract the same value from something else, then you get a 0, and therefore the Z flag is going to be set. And because of that, the two operands really doesn't matter in this case, because you're only checking for equality and not which one is larger. But in this case, you don't have a choice either, because only the first operand can be an immediate operand, so that forces the first one to be 0, and that means the second one has to be resolved. So that basically determines these two instructions in order to implement this particular line in C. So we can do pretty much the same thing with the other one, except we just have to be more careful because we have comparing byte in this case, 10 from CH, which is a single byte location in memory, and JZ to end it, just like that. Are we still doing okay so far with this code? This is actually, the same thing with the end of the loop, because we are looking for the same reason to go back to the beginning of the entire loop. So this is a repetition of what we did on Tuesday. The real tricky part of this program is down here. Okay. So there are two reasons why this is kind of tricky. The first one is how do you multiply by 10. If you don't know how to do multiplication, you can always kind of use add, because 10 is 2 to the power of 3 plus 2 to the power of 1, right? So you can kind of work with that kind of math and then just use a bunch of add instruction to perform this particular operation. But I will talk about the multiplication instruction because that's also going to be useful later on. So that's the first thing we'll address. Okay, how do we calculate num times 10? To calculate num times 10, we have to use the multiplication instruction. And the way it works is you have to put one thing into EAX. That is fixed. Okay, the multiply instruction requires one of the operand in EAX. You don't get to choose it. So in this case, we'll just go ahead and put, I don't know, we can put 10 into EAX. And then the mul instruction, or mul L for multiply long instruction, this is the unsigned version of multiply. We'll take a single operand. In this case, we can use the single operand of num. Okay. Not really sure whether you can take a memory operand in this case, but that's basically what we have to do. If it doesn't take this, we have to move it into a register first and then multiply with the register. So this is really obscure because one of the numbers that we are multiplying is not even represented as an operand. Okay, EAX here is not even represented as an operand. It's not a part of the instruction. It's just implied. The second part is, where do we store the result? That is not specified either. Okay, and that's why you have to refer to this document here, how to multiply and divide. It will talk about the actual details of using the mul instruction. But here I can just kind of give you a quick rundown of how it works. So the mul instruction, and I'll use comment here, will store the product in EDX:EAX. What this means is the product is going to be a 64-bit number. If you multiply 32-bit by 32-bit, you can potentially end up with a 64-bit number. Okay, and that 64-bit number is going to be stored in EDX and EAX. EAX, the way it's represented, means it's going to store the least significant 32-bit of the result of the product. And then EDX is going to store the other part, which is the most significant 32-bit of the product. Okay, this is how the mul instruction works, which is really, really not intuitive because it doesn't tell you, about EAX nor EDX. So when you use instructions like this, divide is about the same. Okay, divide has about the same kind of thing where many of the operands are implied. You have to be careful because of these two instructions. Even if you include the instruction before this, nothing says anything about EDX. So if you're not careful, you can clobber EDX and not know about it because it is not represented in the instructions. And clobbering a register without knowing it can cause big problems. Okay, so what I'll do is I will try to assemble the program first because I'm not 100% sure. Okay, nope, that's the wrong program. So we'll go ahead and read decimal.o, read decimal.s. Actually, it took it, so that's good. Because sometimes, certain combinations of memory operands and whatnot, does not work, which is a big problem. Do you guys still remember the discussion of general purpose register as opposed to special purpose registers? Kind of really early on, general purpose means, the register can be used in any instruction. Special purpose means it can only be used in certain instructions. EAX is generally speaking a general purpose register. Okay, in other words, with a move instruction, you can use EAX, EBX, EDX, ECX, and so on and so forth. But with the multiplication instruction, EAX and EDX are special purpose registers. You don't get to choose. Are we still doing okay so far with the multiplication instruction? Okay. So now that we have the product out of the way, the rest should be pretty easy. So what I'll do is I'll go ahead and implement the program in a certain way, and then I'll explain why it is not going to work. Okay. So you go back to the expression. So let me just go ahead and highlight the expression that we are trying to implement. And you can look at this and go like, well, the second pair of parentheses are not really needed because we're just adding the value of the expression in the parentheses, and it's only a subtraction inside. In other words, we can just get rid of the parentheses and just keep adding CH to the product, and then we subtract the ASCII code of 0 from the entire thing and be done with the whole expression. So I'll just go ahead and write the instruction, and then I'll explain why it's not going to work. So ideally speaking, it seems like we can just do an addl. Well, we cannot do an addl ch to, well, I guess we can. We can addl ch to, in this case, EAX, because remember, the least significant 32-bit is stored in EAX after multiplication instruction. So that seems to be okay. And then we can just subtract along the ASCII code of 0, which can be represented this way. Or if you want to spell it out, it is 30 in hexadecimal. So either form is okay. But I'll just go ahead and use this form here from EAX. So it seems like this should work. Okay, seems pretty easy. Why do you think this is not going to work? Or it might work in some cases, but in general, it won't work. This is the same problem with the compare instruction. What is CH? How big is CH? It's a single byte. And what is the width of the add instruction? It's a long, it's 32-bit. So in addition to the 8-bit that actually has the information that we need, it has 3 extra bytes. And those 3 extra bytes, can we guarantee those to be zeros? Cannot, okay? So this is not going to work, okay? Most of the time, this will end up with a value that is much larger than what it should be because CH itself is only an 8-bit number, which means unsigned, it can only represent up to 255. But when you use add long like this, it becomes a 32-bit number, which can be up to 4 billion something. Okay. So how do we fix this problem? Sorry? Add B. Okay, well, let's see if add byte is going to do to fix the problem. Now, add B is not going to work because this won't even assemble. It is not going to assemble because the width of the operation does not agree with the result. Yep.
Move 0 to EAX and then add.
Not EAX because EAX is currently in use. So you have to, but the idea is the same. Yes, I think I get your idea. So the idea here is to use another register, okay, so we can just move a 0 out EBX, okay, whatever, you can pick ECX or EDX, it doesn't matter which register you pick. I'm just picking EBX here. And then what you do is you move byte CH into %BL. Now, if you look at these two instructions together, okay, these two instructions, it's basically doing a sign extension. In other words, it's turning an 8-bit number into a 32-bit number with the correct sign extension. Does it make any sense? Now this only works if it is unsigned, because if it is signed, it doesn't do the sign extension correctly. It doesn't replicate bit 7 all the way throughout the other bits. But since in this case the CH itself is unsigned, it will work just fine. Because we are basically starting out with all 32-bit being 0 in EDX, and then we only change the least significant 8-bit to CH. So the rest are guaranteed to be 0 in this case. So that means when we get to the add instruction, we can go back and use an add long instruction, but we won't be using CH directly. We'll be using the signed extended version of CH, which is currently stored in EBX. And the rest of the program will work because subtracting the ASCII code of 0 from EAX, the immediate operand can sign extend automatically. So that part is not an issue. And then when this is all done, we have to store the result back into num. So a single move instruction from EAX back to num will get that problem, it will get it implemented. So I think this program is ready, okay? Maybe, maybe not. Yep.
Yeah, could you explain again, like after the product, you get the product. What's an EDX?
EDX is the most significant 32-bit of the 64-bit product. Because when you multiply 32-bit by 32-bit, the end result can be up to 64-bit. And the Intel instruction set decides not to lose the most significant 32-bit, and it is represented in EDX. Now, most of the time, you toss it away. In other words, if you were to do the same program in C and C++ and everything is 32-bit, the most significant 32-bit is just completely truncated. I mean, it's just lost in the process. But in assembly programming, we actually do have a choice of whether we pay any attention to the most significant 32-bit of a product. But the bad part is EDX does not appear once in both instructions. So it's really easy to kind of miss that part and have some prior use of EDX come to get to the multiplied instruction and have EDX destroyed in the process.
So if it did get, let's say if it didn't go into EDX overflow, so would that mean that EDX is all zeros in that case? Like,
if the product does not require, then yes, it will be all zeros basically.
Okay, so you can check to see if it overflowed pretty much.
Yes, you can check whether the result of a multiplication requires more than 32 bits to represent. Yes. Yep.
If you were to do that byte for CH instead of AL, would that not handle the overflow question correctly?
It will handle the least significant 8 bits correctly, but what if that has a carry?
That's what I was asking. Would be able to handle the carriers?
There's no easy way to handle a carry because you can use that with carry byte in the next instruction to AH. Okay, but that itself can also generate a carry to bit 16 of EAX, but we don't have a way to refer to bit 16 and up of EAX. It doesn't have a name, and therefore there's no way to propagate that carry any further if it does happen. So that's why this is pretty much the only way to do it. I understand what you're talking about here. It's just that we can't do it because we don't have a name for bit 16 to bit 31 of EAX. All right, so I think we are ready. So let's go ahead and test the program and see whether it is doing what we think it should be doing. Well, let's create a little test file here, test.in. Well, it has a number already, 586. We'll just go ahead and use it. GDB, read decimal, put a breakpoint at the very end. So we'll put a breakpoint at loop exit. When the loop exits, we want to check everything again. Run the program, but redirect the input from test.in. Having a test file like this and being able to redirect has several advantages. One is there's no confusion between, oh, am I specifying the command, to GDB itself, or am I feeding into the program? So there's no confusion at all, with this type of approach. But the second thing is you can use the same test case consistently time over time over time. Or if you can think of certain test cases that you want to use, you just store those test cases into different files. And then you can write your own script to basically test your own program based on all the test cases that you can think of. So this is definitely a good approach of testing your program. So run the program, okay, it doesn't crash. So now we want to take a look at result. Oop, that won't work. Print result, and it's not working. Nope, it's not stored in result, is it? It's stored in num. Result is the return value of the read call. Num is the value of the number that we are representing internally. So this does work. Now, if you were to put a breakpoint at the end of the loop, so at the end of each iteration, you check it. After the first iteration, you will end up with 5 in num. After the second one, you will end up with 58, and after the third iteration, it will be 586. Right. Do we have any questions about conversion? In other words, how to read a decimal number and then represent it internally as a base 2 number? No questions? So we had one program to convert, to print a number as a base 2 number, and then we have another program now to convert a number from base 10 to the internal representation, which is base 2. Any questions about this stuff? If there are no questions, I can give you the next homework assignment. It's not going to be tonight. I'll go home and then work on the next homework assignment, but it will be based on input and output system calls. We can do string search. Yep.
So there's no way to just figure out, 586 somewhere in memory when it's being looked at is at the binary representation of it. There's no way to just grab it right there and just plug it out.
Nope. This is what cin has to do too. If you have cin in the C++ program and you have cin greater than to a unsigned long variable, eventually it boils down to this kind of operation. Because it still has to go through the base conversion process. It still has to go from a base 10 number represented in ASCII code of the digits, and it has to convert that into the internal binary representation. It's just that in C, if you use cin, there's a whole lot of other stuff going on, like buffering and whatnot. So it's not going to be as easy to understand as this. Okay. Are there any other questions about this particular program? No questions? All right. If there are no questions about this, then we'll move on and get started with topic number 7. Topic 7 is a much larger topic in many, many ways compared to topic 6. So I will turn the highlight onto topic number 7. That's kind of like a bookmark, so we remember where we are in the notes. So we are now on to topic number 7. Turn on that little light bulb. It starts with the discussion of the stack, and then we'll talk about the call and return instructions. And then we'll talk about the make program, because we'll be using multiple files in a single project. And then we'll talk about the use of the stack in assembly language programming. And then, after topic number 7, we have topic 8. Topic 8 seems pretty simple. There's only one single topic there, call frame. But call frame all by itself is a pretty long topic. It really requires all the skills that you have built up to this point, including some of the addressing modes that we haven't seen for a while. Like the based addressing mode is going to come back in this particular topic in topic 8. Okay. So this is just a preview of what is coming. So we'll go step by step, go start with just the stack. The stack is basically a data structure that has a LIFO characteristic. LIFO stands for last in, first out. In other words, with a stack, there are two types of operations, two types of really, really basic operations. You can say, I want to store something, or I want to retrieve something, okay? So that's pretty easy, right? I mean, you have a little container of some kind, and then you can say, I want to put something into the container. I want to put another item into the container. I want to put the third item into the container. But when you retrieve items from the container, which one are you going to retrieve first out of a general container? Well, with this one, it is the last one, okay? With a queue, which is first in, first out, it'll be the first one. Okay. Interestingly, last in, first out doesn't seem to be very useful in computers because a lot of times when we talk about computer stuff, we use first in, first out. Like buffer is first in, first out. Because when you watch a movie from Netflix, okay, the frames, are basically buffered up, as much as possible, so that you don't, encounter, problems when you're replaying the movie. But it doesn't make any sense to use last in, first out in that case, because you'll be watching your movie, backwards at times. That would be kind of troublesome, right? So first in, first out seems to make a lot more sense. When you are waiting in line at Costco or Walmart, okay, do you want that line to be last in, first out?
No.
Probably not, especially with Walmart, because it will wait. You have to wait until the end of the day, to get out of the store, if it is last in, first out. But if it's first in, first out, then it will still be served in the order of arriving at the queue, at the line. Okay, so last in, first out doesn't seem to be very useful at all in general. Unfortunately, there are things that are last in, first out when we do not want it to be last in, first out. Okay, let's say you're loading up a U-Haul truck, and this is a normal U-Haul truck. Okay, I know you can design the U-Haul truck that's different. So let's say you're loading up a normal U-Haul truck, and you accidentally put the map of the destination as one of the first things that you put in the truck, and then you load it up with everything else, and the bicycle is the last one. Okay, and then you slam the gate shut. And then you walk up to the to the driver's seat, and then you just remember, oh, the map is in the truck. How much stuff do you have to dig through to get to the map?
All of it.
All of it, right? Because it's last in, first out, right? And whatever you put in first is the last thing that you retrieve from the U-Haul truck. Your refrigerator also has a native last in, first out nature because it only has one door. Okay, what happens when you go to a grocery store and buy new things and need to put it into the refrigerator? How many people would go through the trouble to empty out the entire refrigerator first, put in what you just purchased, all the way push it all the way into the refrigerator, and then put back whatever was in the fridge to begin with back into the refrigerator? How many people actually do that? You? Wow.
I have a very small fridge.
Okay.
And it mainly holds Dr. Pepper.
But most people don't, okay? So that means whenever you buy something, you put it in the refrigerator, the freshest stuff is the outermost, and then the oldest stuff is all the way to the back. But when you access and try to get your milk or your bread or your eggs, you're getting the stuff that is fresh that you just bought yesterday. What about that stuff that you bought 3 weeks ago?
Forget about it. It's green.
It becomes what we call a mold garden. Okay, colorful, purple, green, and all kinds of color, all the way in the back of the fridge.
I don't know, my fridge is random access.
The fridge is random access. Now you can turn it around. It's relatively easy to turn it into a queue of first in, first out. What you need is a carousel. So that way, and 2 doors. Okay, having 2 doors definitely help too.
We put doors on both sides of the fridge. Put doors on both sides of the fridge.
And then have
Two
rollers,
separate
right?
sides.
So it has to roll, keep rolling. You put things in one direction and you retrieve it from the other direction. Okay, so I think we have a pretty good understanding of what is first in, first out versus last in, first out. And in computer science, last in, first out, or what we call the stack data structure, is actually very important, very much as important as FIFO or first in, first out, maybe more important compared to first in, first out. It has to do with the languages, the computer languages that we have to deal with on a daily basis, like C, C++, and so on and so forth. When you get to, there's a class called computation theory, okay? Then we'll talk about different types of what we call automata, like a finite state machine, a stack machine, Turing machines, and so on and so forth. And you will find that a finite state machine is useful, but it's kind of limited of what it can do. A finite state machine can recognize what we know as regular expression, okay? And I think last time we kind of talked about regular expression a little bit, and some people have some experience with regular expression. So regular expression does not need a stack at all to parse and to recognize the pattern. A programming language like C and C++ cannot be recognized by a finite state machine because there's nesting. Every time you have nesting, like curly braces and stuff like that, you cannot use anything like a finite state machine. So in that case, you need a stack machine, what we call stack machine. And that's why stack machines are extremely useful in computer science, especially when it comes to parsing the syntax of a programming language. Okay, so that's why it's really useful. We use the stack all day long without really realizing it. Because when you invoke or call a subroutine, and that subroutine calls another subroutine, and that subroutine calls another subroutine, the return address of all those calls, they are also arranged in the last in, first out fashion. Okay. For those of you who took cisp310 from me, you may remember that we keep track of the return address, when we invoke a subroutine. The construction or the allocation of the return address and the deallocation of those columns also follow the order of last in, first out. So we have seen a lot of last in, first out already, even before we get into this class. Okay. So what we'll do is I will start with a sample program just to illustrate the nature of last in, first out, and then we'll go in and talk about the stack pointer and what actually happened when we push something into the stack and what actually happens when we pop something from the stack. Okay. So we'll create a folder for today. Today's 0404. And we'll have a first sample program called stack1.s. So this is going to be an actual program that will compile, that will assemble, link, and run. We start with .text. Global start, underscore start. And the push instruction is basically putting something into the stack. The pop instruction is to retrieve something from the stack and put it into a register, but for the most part. When you push, you can push just about anything. Anything that can be the first operand of a move instruction can be the operand of a push L instruction. Okay, so because it kind of works the same way, except you're not putting it, you're not storing it in the destination, you're putting it into the stack. So you'd say push L, I'll give you one example here. Push L, a constant of 10. Okay, this is 10 in decimal, represented as a 32-bit number. You're basically storing a constant of 10 in the stack. Yep.
Your notes doesn't have push L as one of the push operands. Are you able to specify length that you're pushing then?
Yes, you can.
Okay.
Yep. So the next one, let's say we push, 145, 156, and then the last one. Well, let's make it the last one that push W instruction, just so that we know we can push, things of different width onto the stack. So the last one will just push, 0x 2e, right there. Okay. When you retrieve items from the stack, you use the pop L instruction. The pop L instruction will require an operand that can only appear as the second operand of a move instruction because it is representing a destination of storing something that you just retrieved from the stack. Okay? So in this case, we can use pop L, pop W, because you have to match it. Okay, the last thing you push has to be the first thing that you pop. So the width has to match if we are to expect 2e again in the destination. So we'll put this one into, let's say, AX. The next one is long, we put it into EBX. And then the last one is also long, which we'll put into ECX. Okay. And that's the entire program. I'll just go ahead and finish it anyway. That. So this program is going to be useful for a few, in a few different sessions, but the first one is going to be pretty simple. In the first attempt to understand the stack, all that we'll do is we'll just observe the push and the pop instruction from the register's perspective. So LD-O stack 1.0, GDB stack 1. Okay. We'll skip lines 4, 5, and 6. In other words, we don't really care what the push out instructions will do. We'll focus on lines 8, 9, and 10, and basically say, well, what am I going to get in AX? What am I going to get in EBX? And what am I going to get in ECX? Okay. Run the program, single step the pop out instruction, take a look at AX, and it has 2E, which is the very last item that we put into the stack. Single step the next instruction, pop out EBX, IR EBX. It has 156 in decimal, which is the second thing that we push on the stack. Single step the last instruction, take a look at ECX. It is the very first item that we push on the stack. In other words, the last in, first out ordering is observed here. The first item, the first value that we push on the stack is the very last one that will be popped from the stack. Are there any questions about this particular trace? This particular example of using the stack? Yep, go ahead.
So can you push 32 bits and then pop to 16 bits?
Yes, you can. You can definitely do it in a different order, and we will do that too. We'll mess up this program.
So is that like little endian as it pushes onto the screen?
Yes.
Okay.
But before we can talk about that, we have to talk about how things are actually stored on the stack. So we'll defer that discussion. That's a very good question to ask. But we'll defer that discussion until we understand how things are actually put onto the stack. Okay. Yep. Go ahead.
What happens if you pop when you haven't pushed?
What if you're trying to retrieve something when you did not store something into the stack?
Will you get an error or will you just get something?
It depends, okay? Because by the time your program has control, something is already pushed on the stack by the operating system. So you'll be retrieving that something.
So you're retrieving garbage.
Something that you did not push, not necessarily garbage, but it's not something that you push on the stack. Yep.
Pop is destructive because it takes the last item off the stack. So if you're popping something that you didn't push on there, aren't you going to be?
Can you peek?
You can peek, but we cannot talk about that until we talk about the stack pointer.
Yeah, sort of. Where is the stack? Like where is it?
That's a good question. So that's what we're going to talk about next is the stack pointer. So this program is very superficial at this point, okay? Because we are not looking into the stack pointer, and I'm not explaining what a stack pointer is and how it does all these little things. Yep.
Is the program all scripted in stack pointer, or does it kind of make one and then it uses that as a kind of a memory storage?
By the time your program has control, the stack pointer is already initialized by the operating system to the right point in memory. So you can always, you're guaranteed that the stack pointer is starting at the correct place when you start your very first instruction.
So then this stack is shared amongst all programs? Or
No, each process has its, okay, I take it back. Each thread has its own stack. So even if you have a single process and you're using multi-threading, each thread has its own stack. But if you have one single thread within your process, then you only have one stack. Okay? But we are not going to talk about multi-threading in this class, so for our discussion, you can say one process has at least one stack. Okay? Are there any other questions? So that means if you run the same program twice in parallel so that both instances are running at the same time, then you have two processes corresponding to the same executable, and as a result, you have at least 2 stacks in that case. Okay? And the two stacks are also completely independent to each other. Okay, so the next question is, how does it get this magic done? I mean, this seems kind of interesting, because where are we actually storing these constants, 10, 156, and 2e in hexadecimal? Okay, and how far can we push? I mean, how much stuff can we push on the stack before it runs out of space? Okay, so what we'll do next is to talk about the stack pointer. So I'm not going to talk about details yet, at this point. So I will go ahead and okay, this is already going a little bit too far. Okay. So what I'll do is I'm going to quit this program for now and talk about what a stack pointer is. A stack pointer is basically a pointer. Okay, it's a register. ESP is the stack pointer. It is basically what we call, a general purpose register. In other words, you can use it in a move instruction if you want to, but it serves one particular purpose. It is called a stack pointer because it is always pointing to a particular point on the stack. And has anyone read the notes ahead of me? No. Okay. Okay. The stack pointer points to the very next location for the next push instruction. Okay? It's pointing to the location that is available for the next push instruction. Whatever is available next. Okay? All right.
Can you change that?
You can change the stack pointer directly, yes.
So you can treat the stack however you want it, really want.
You can, yes, you can
Just treat
move
the
your stack
stack.
around if you want to. Yep, and therefore,
It's not
things
really
can
a stack.
happen,
Yeah.
yes. Bad things can happen when you change it, in a way that is not good. Okay, very, very strange things. Okay, so what we'll do is we'll run the same program again, but this time we'll take a look at ESP and see how it's changing with the instructions that we have already traced in the previous attempt. So we're going back to stack 1, starting from the beginning. But this time I'll start my trace from line 4. In other words, I'm not starting to trace, I'm not stopping at line 8. I'm stopping with the very first instruction, the push L instruction. And I'll run the program. So this is right before the push L $10 instruction here. I will take a look at ESP. ESP, or the extend enhanced mode stack pointer, for our discussion purposes, we just call it a stack pointer, has a particular address. It's pointing to a location BFFFF That's where it's pointing right now. That location is actually representing the next location where you can store an item. Okay. So what we'll do is we'll go ahead and do our push instruction. I take it back. I made a mistake because there are different architectures do it slightly differently. In this architecture, this is the address of the last item pushed on the stack. Okay, so let's do a correction here. The stack pointer points to the last byte of the last item that you pushed. So somebody pushed something to this location, but it's not my program, so I'm not even going to bother to look at what is at that location at this point. So let's take a look at this location, and then we'll single step the program. Single step the program, take a look at ESP again. We know it's changed, but how was it changed? Was it increased or decreased? And if so, by how much? Well, first of all, did it increase or decrease? It decreased, okay, by 4 bytes. Okay. Now the 4 bytes, you can probably explain that because it is a push L instruction. We're pushing 4 bytes, and therefore 4 bytes is moved by 4. But it's not increasing because we think, oh, if you want to store something, the pointer has to increase, not with a stack. Okay, a stack is what I call growing backwards. In other words, it starts pointing at a high location. The more stuff you push, the lower the address becomes. Okay, and there is a good reason why it should be doing it like that and not, doing the more intuitive way of, going forward. Okay. And remember what I just said? The stack pointer points to the very last item that we push on the stack. So that means if I examine that location, what it is right now, what the stack pointer is currently pointing at, BFFFFAEC, I should find that constant of 10 again. Right? Okay, so let's go ahead and see if that's what we're going to get. We'll use the examine command, okay? And because the 10 is a decimal number, we'll use either U or D, okay? D for signed decimal and U for unsigned decimal. It is also a 32-bit thing, so we have to use a W for word in the debugger. And we can do a little shorthand here. So instead of copying 0x BFFFFAEC, I can just use the special internal variable called $ESP, because it really represents the current value of the stack pointer. And we'll take a look. And sure enough, it has a content of 10. Okay. Which is not surprising, okay, because that's exactly what we just pushed on the stack. And according to my corrected definition of the stack pointer, it points to the very last item that we push on the stack. So that really kind of gives you an idea of what it should do next, because the next instruction I'm going to execute is pushing the literal constant of 156 in decimal. So single step, take a look at the ESP again. What do you think it's going to be? Just name the last digit. I mean, the rest of it will be the same. The last digit of the stack pointer should now be 8, exactly, because C minus 4 is 8 in hexadecimal. Okay, so we'll take a look and confirm that observation. Yep, definitely. And if I were to examine the location where the stack pointer is currently pointing to, what should I expect? I should expect 156 in decimal. Okay, that's exactly what's happening. Okay. Well, since we're here already, might as well just single step the push W instruction and then do the same thing, but this time we should only be looking at the half word instead of a full word, and this is going to be displayed in hexadecimal because that's how it was represented in the source code, and we get 2E back. Okay. That's kind of interesting. How many bytes have we pushed all together up to this point? We have a push long, and then a push W.
10.
We have 10 bytes. So what if I were to display all 10 bytes byte by byte at this point from memory? Let's see what we are going to find. So we'll change our examine instruction to examine in hexadecimal, single byte for each item, and we have 20 of those things, starting at where the stack pointer is pointing at. This is what we're getting. Is that making any sense? Well, not 20, 10. Intended 10, but I typed in 20. So, because this is including some stuff that is not what we pushed, so this is better. Okay. Is that making any sense? The stack pointer points to the very last item that we pushed on the stack. Is that still consistent with this trace here? Yep, it's okay, because 2E00 is the last thing that we push on the stack. The one thing before that is 156 in decimal, right? 156 in decimal is 9C in hexadecimal, and those are these 4 bytes. And the very first item that we push is 10 in decimal, and those are these 4 bytes. So that means when you push something on the stack, you can always retrieve something that you pushed earlier by adding an offset to the stack pointer, and then be able to basically peek things that are not currently pointed to by the stack pointer. And that's why the base addressing mode is so useful, because it allows you to peek at things that were pushed earlier by some other code. Are we still doing okay so far with the stack pointer and the content on the stack? Okay. So you can already kind of imagine what happens when you do a pop instruction. The next instruction we want to execute is a pop W instruction. What a pop W instruction is going to do is it will go to where ESP is pointing at and retrieve those 2 bytes, copy those into AX in this case, using the little endian convention. And then it will increase the stack pointer by 2 so that the stack pointer will be pointing to this byte after the instruction. Is that making any sense?
How much space is allocated for the stack?
I think it can go all the way down to 8 and then followed by all zeros. So it's pretty huge. I mean, it allocates, you know.
You typically don't have a problem with running out of stack space.
Unless you have an infinite loop implemented in a recursive fashion, then you can easily run out, right? I once tried to write a program like that, you know, to see, you know, how far it can go, and it took a little bit of time to get to the end. Okay, so let's go ahead and single step this particular instruction. We'll single step the pop W instruction. And the first thing we'll do, we already know that AX is going to end up with, you know, 002E, you know, as a value. But what we want to do is to take a look at ESP. Because you can see that ESP, oh, I forgot to track down ESP, you know, after the last push instruction. Did I? Okay, let's see here. I single step, and this is the instruction where I forgot to actually look at the. Okay, this is the last address of the stack pointer. Even though I did not display ESP explicitly, the memory dump actually, you know, effectively showed the address. And this is what it is right now. And you can see it has increased by 2. Okay, well that all makes sense, right? I mean, the stack pointer is pointing to the next item that you can pop on the stack, or the last thing that you push on the stack. But what happened to those two bytes, the 2E and the 00? Do you think those are still at the same memory location, or do you think they are gone?
I think they're still there.
They're still there. Exactly, they're still there, except the values cannot be guaranteed at that point anymore. Okay, I cannot really demonstrate it, you know, with a program like this because we're running in a protected operating system, which means when interrupt happens, it's not going to clobber this stack, because when interrupt happens, the hardware will try to save the current execution location on the stack, and then it will go to the ISR, or the interrupt surface routine, which means whatever is before the stack pointer or at a lower address compared to where the stack pointer is pointing at can change over time. Yep.
If this is a stupid question, it's fine, but who tracks allocation?
Who tracks
Or what tracks allocation?
allocation
Global
of
memory allocation. Like, what does it mark to say, okay, we're not using this stuff anymore? What
the
does it mark?
operating system?
Okay, so
There are 2 levels of memory allocation and deallocation.
Yeah.
When you're talking about, you know, large chunk memory allocation like the stack itself, and also the static portion of your static variables, the operating system is doing the allocation. In other words, the operating system will allocate memory from its memory space, and it will remap the memory to your program. So that's why your program always sees that, oh, I'm always starting with this memory location. That part is done by the operating system. So when you run out, then your instruction will try to access a location that does not belong to you, or it has not been allocated, and that's why you get a segmentation fault in that case. Now, when you're talking about new delete in C++ or malloc and free in C, then you're talking about a library managed heap that is mostly managed by the application itself.
Okay.
Until the heap runs out, then the heap manager can ask the operating system, can I get another chunk of memory? And if there isn't another chunk of memory available, then the operating system can come back and say, okay, here's another chunk.
That's all automated. I've never had to deal with the heap, so I'm assuming that's automated.
That's done by the heap management libraries.
Okay.
So that's why when you do a malloc, it will automatically go through all these motions, and when it cannot malloc anymore, it returns a null pointer to basically say, no, we are running out of memory.
Okay. So in this situation, since everything's static, nothing's changing real time, the program knows from compilation exactly how much space you're gonna need.
No, it does not.
It does not.
It does not because
I figured just for this program, we could add something where we have input and things could.
well, with this program, we can manually analyze the program
Yeah.
and say, well, there's one push long,
Yeah,
two
okay.
push longs, and then one push W instructions. So therefore, we are only using up 10 bytes on the stack. But that's completely by manually analyzing the program. If you have a C program, you cannot really know how much stack space it's going to consume because you can have recursion.
But we could do that here too.
Yes, exactly. We can have recursion in assembly programming as well, and that's why when you run out of stack space, when you have recursion, it's a hard crash. There's no way to recover from that because basically you just run out of resources and it causes a segmentation fault.
Okay. So even though we're protected, we could do stupid things.
Right.
That's also-
Protected means protected means other applications are protected from your program's misbehavior.
Yeah, but I'm not protected from myself.
So you can still do things to sabotage your own program. It's just that those actions cannot affect the operating system nor the other programs.
Okay.
Yep. All right. So are we doing okay so far with the stack discussion? Okay. All right. So let's go back to this program. We'll go back to the source code. And this time I'll copy the original source code to stack2.s. And in stack2.s, we'll go back to the same code here and say, but what if I don't have a push instruction? What if I don't have a pop instruction? Can we implement exactly the same thing as what this program has, but using only instructions that we already know? Okay? In other words, we look at these instructions and say they are cisp instructions, and we have a RISC architecture which does not offer these same instructions. Can we still accomplish the same thing with things that we have learned up to this point?
Yeah, but we gotta allocate the memory ahead of time.
Well, the memory allocation is done by the operating system in either case, so it's not going to be, that's not our responsibility.
Yeah, we have to create.
We have to move the stack pointer.
Yeah. Okay.
Right, we have to move the stack pointer, but the region that is that is available for the stack is already pre-allocated. Okay, so we take a look at one single instruction. So we focus on one at a time. Okay, so we'll push the other one, move the other ones out of the screen so we can focus better on the one that we are dealing with. So we are saying that we cannot have a single instruction to do a push $10. Can we do something like that with the instructions that we already know? Well, let's figure out what it's supposed to do first. Okay, the first thing it will do is it will copy the 32-bit bit pattern of 10 in decimal to where ESP points to. Then the second thing it will do is to move the stack pointer, by the other way around. It has to move the stack pointer down by 4 bytes. And then it will copy the 32-bit bit pattern of 10 to where the stack pointer points to. Because remember, my adjusted definition of the stack pointer is it points to the very last item that you just pushed. And this will fit that requirement. So now we look at the English description of both lines and say, well, do we have any instructions that can move the stack pointer down by 4 bytes? How do we do that?
You add
You can use add or subtract, either way it works. So you can say add L, -4 to ESP. In other words, you're effectively just adjusting the stack pointer so it is 4 less than what it used to be. Is that making any sense? Because we are just moving a bookmark back by 4 pages. Okay, there's no massive memory move at all. We're just moving the bookmark that separates the allocated portion of the stack from the unallocated portion of the stack.
And if we were to examine line 1, we would see that ESP is pointing somewhere that the operating system told us, here's cool.
Right, because it's pointing to the very last item that the operating system pushed before passing control to _start. Right. What about this instruction here? What about this next one? Copy the 32-bit bit pattern of 10 to where ESP points to.
move L, or
Okay, move L.
10
10 to
ESP.
like that. That's gonna clobber ESP, so I will end up with an ESP pointing to location 10. Put in the parentheses, and we are all done. The parentheses turn this operand from a register operand to an indirect operand, which means we're only using ESP to tell me where to move $10 to. And that really fits the description, okay? Copy the 32-bit pattern of 10 to where ESP points to, okay? So that will do the trick. The rest, the other two instructions, I think we know how to do that already. So we're not too concerned about the other push L and the push W instruction. Let's go ahead and take a look at the push pop W instruction and try to see if I can implement this using instructions that we know already. This is exactly the opposite of what we had earlier. The first thing we have to do is to copy, in this case, the 16-bit thing pointed to by ESP to AX. Because by definition, the stack pointer points to the very last thing that I push on the stack. So I will just have to copy whatever the stack pointer points to the destination, AX in this case. Is that making any sense? Okay. And then the next thing I have to do is to say, oh, you know what? Whatever is at that location is now retrieved. I do not need that on the stack anymore. So I'm going to change the stack pointer up by 2 bytes to basically say, oh, those 2 bytes are now deallocated. That space is unallocated, at this point. So I just have to say, move the stack pointer up. When I say up, it means increase. When I say down, it means decrease by 2 bytes in this case. So how do we do this? Copy the 16-bit thing pointed to by ESP to AX. Move W, 16-bit, indirect ESP, because that's where the stack pointer is pointing to register AX in this case. Move the stack pointer up by 2 bytes. Is just add L, $2 to ESP. And those are exactly those are the not instruction but the microcode that the processor uses in order to implement the push and the pop instructions.
So push and pop are just macros?
Yeah, for the most part. In fact, when you look at the i386 instruction set, they are all basically macros. The really core part of your Intel or AMD processor is actually a RISC architecture. And it's basically following these microcode to implement what we see as the i386 instruction set. And that's why it is so inefficient, because it is going through multiple levels of translation and overhead in order to give us the pretense of this is still an i386 computer or processor. Yep.
And all that's to maintain backwards compatibility of everything.
All of that is to maintain binary backward compatibility. Yes. In other words, we can basically keep the same object code, and it will still execute on on modern processors. So if you have a program or an entire hard drive with an operating system installed that was intended for the i386 processor, it will still run fine with an i7 processor, top of the line i7 processor.
So if we scrap all that and we did maintain backwards compatibility, like our processors could be like multiple times faster probably?
For the power consumption, that they're consuming, they can do a lot more processing, yes. So they can be more power efficient if we do not have to maintain the backward compatibility. And backward compatibility, binary backward compatibility, is not something that is a true necessity. Because if you look at Linux, how many different architectures are supported by Linux?
Many.
A lot. Okay, we have a lot of architectures that can run Linux. Even architecture that are still on the blueprint, that is not fab yet, they can run Linux already in simulation. And that's because Linux, for the most part, has a very small percentage of the operating system written in assembly language. For the most part, it's written in C in a portable way. Okay. So that means the architecture should not have that much implication when it comes to the operating system nor the application, because you just recompile the program to a different architecture. Basically, what they have to do is to retarget GCC first. So GCC, the back end of GCC will generate object code that is specific to an actual hardware implementation. But that really is a small percentage of GCC itself. So in order to retarget GCC for a different architecture, yes, there is work involved, but it is not that much work. And in terms of porting the Linux kernel from one architecture to another architecture, yes, there will be work to be done because of the differences between architectures, but once again, it is not all that much. And that's why Linux can be ported from one architecture to the next with relative ease. Is because everything is kept in a way where you can easily retarget the entire tool chain to a different architecture. So the only reason why we do not have something like that is because Windows is not designed that way. In other words, for whatever reason, Microsoft does not have the ability to retarget their applications nor their operating system to run in a different architecture without having to spend a lot of resources to retarget their tool chain.
So basically, any PC is never going to have that. Well, I mean, this is super specialized for Linux only people.
Right. But the Linux market is too small,
Yeah.
and that's why they would never have an architecture that is efficient like that. It took, how many decades did it take for Microsoft to come up with their ARM-based Windows system? Windows 8 has a version for the ARM architecture, and how long did it take? That pretty much answered that question, right? And even with the ARM architecture, it's not completely compatible because Microsoft Office for their ARM architecture for Windows 8 for the ARM is not the same as Microsoft Office for the Intel architecture. Okay, they have to shrink it because they can't fit the entire program onto an ARM architecture for whatever reason. I don't know. I have no idea. But if you get a Raspberry Pi which runs on the ARM architecture, you can run a Linux system. Basically all the tools in Linux, you can run it on the ARM architecture just fine. So we are this is beyond what I can understand, so I cannot really talk about it. But the bottom line is, if we do not have to waste silicon for binary backward compatibility, for whatever the power consumption is for the i7 processor, it can do more with that kind of power. All right. So are there any questions about the push and pop instructions? No questions about the push and pop instructions? How about their equivalent instructions using instructions that we already know? No questions about that? Wow. All right. Well, we are definitely moving forward pretty quickly here. Okay, so this is about the same thing. We talked about this already. So what I'll do is I'm going to mess up this program. Okay, this is stack 2. I'll mess up the program called stack 3. I'll leave it up. I'll let you guys try to think about what this program is going to do just because of that little mess up. So stack 3.s, and what I'll do is I'm gonna change the order of instructions just a little bit, and you guys will have to help me figure out what will be in EBX, ECX, and AX in this particular case. And we'll try to work this out on paper. Okay, we have about 4 minutes. That should be enough time. No, seriously, we have enough time to do this. Okay, so what we'll do is we'll go through these instructions by hand and figure out the memory locations on stack at this point. After we'll do it step by step. The first push out instruction is going to push in the same orientation that you see in the memory dump. You will see 0A, 0. Okay, since these are all hexadecimal, we'll just use 0A, 0, 0, 0, 0, 0, 0. It will push these 4 bytes on the stack. The second instruction will push, it's 9 something, right? 9 what?
9C.
9C. Okay, 9C, 0, 0, 0, 0, 0, 0. And this one is pretty obvious. It's 2E and 0, 0. Okay. So at this point, if I were to spell out the memory content on the stack, leftmost being the lowest address and rightmost being the highest address, we will see 2E00 at the lowest location, 9C000000, the next one, and then the last one, which means the highest location, will have 0A000000. That's the content on the stack at this point, and at this point, the stack pointer will be pointing to the 2E because it is the very last thing that we push on the stack. Are we still doing okay so far? This is actually what we observed already with an earlier trace. So with the pop-L instruction, it's just going to the stack and say, give me 4 bytes. And then I'll adjust the stack pointer by 4. That's all it's going to do. It did not know that the last 4 byte on the stack was pushed, half of it was pushed by one push L instruction, and then the other half was pushed by a push W instruction. It does not know how it came, how the stack pointer became like this. So this means after this instruction, the stack pointer will point to, okay, well, this is the lazy way to do it. I can do it like that, which means EBX is going to be 2E009C00. But because of little endian, we have to flip the bytes around a little bit so that 00 becomes the most significant bit, 9C becomes the second most, the most significant byte, 9C is the second most significant byte, and then 00, and then 2E becomes the least significant byte of EBX. Okay? All right, so now that we know this, the next pop-L instruction will move the stack pointer like this, which also means ECX is going to pick up the next 4 bytes, which means it's going to pick up 00, 0A, 00, and 00. Right? This is including the flipping of the MSB and the LSB. And then the very last one is going to be pretty easy because 00 is 00 anyway. So AX is going to end up with a value of 0000. Okay, so that's what we need to do. When we try to understand what is going to happen on the stack, because we want to predict what's going to happen in a GDB session first, and then we use GDB to verify that is actually what is going to happen. We have 10 seconds to go. I think we may have just enough time. If I just borrow 1 minute of your time, we can finish this. So we are only interested in this case on line 13, 16, and 19. So we'll go ahead and run the entire program, single step, IREBX, and we get 9C002C. Because it doesn't print the leading zeros in this case. Single step the second instruction, look at ECX. It has 00, 0A, 0000. And single step the last instruction, look at AX. And it has 00. So so we modeled the execution of the instructions correctly in this case. All right. So we have two seconds to spare of the 1 minute that I borrowed from you. All right. So I'll see you guys on Tuesday. I will give you a new homework assignment over the weekend, basically using the system calls input and output.